Hello, I am Grigore. I'm the founder and CEO of Pi Squared, and I'm going to tell you what we do at Pi Squared. The TLDR is that we want to bring all programming languages to the blockchain, to Web3. So you can write smart contracts in any programming language of your choice. So Pi Squared, the keyword defining Pi Squared is universality. So it is a universal protocol and modular in the sense that you can program in any programming language, you can settle anything that is provable with any proof system of your choice, and in the end, you can achieve consensus with a very fast consensus protocol. You can even bring your own language, BYOL. You can bring your own language. You can define your own language specific to your application, and then plug and play it. Then write smart contracts in that language on the chain. And you will not have to change anything in the network in order to support a new language. Then you can prove computations using any proof system, be it mathematical or cryptographic. And once you have a proof for the claim, then you can settle it once and for all. And then I will not talk much about consensus today because my goal is to show you how you can bring languages to your blockchain, any language to your blockchain, even though your blockchain doesn't use that language, and you already have a consensus there. But there is also a very interesting consensus protocol that I would love to talk about at some point, but not here. So unfortunately, we have a very small number of programmers in the blockchain space, right? Only like 8,000 and something in Solidity, only 20,000 something in blockchain in general. We want to expand this to millions. We want to bring all the Web2, the tens of millions of Web2 developers to Web3, and in the future, many more. AI programs and everything in any language to run as a smart contract. So to make this a reality, we have three orthogonal innovations in Pi Squared that together are more than the sum of the parts. So by the way, feel free to interrupt me and ask me questions. I like to make this interesting and interactive. So the ULM, first of all, is the universal language machine. It is what allows you to write smart contracts in any programming languages, what allows you to bring new programming languages to the blockchain, to your blockchain. The USL, Universal Settlement Layer, all the U's come from universal. The USL is what allows you to prove, to generate proofs and to settle claims once and for all in any language, in particular executions of programs in any languages. And the Universal Consensus Protocol is a generalization of what consensus was meant to be from the very beginning, consensus of values, not on sequences. You don't really need sequencing for all applications. Like if you have a voting application, you don't need the sequencing of the votes. Okay, so Pi Squared will allow you to also have more relaxed consensus that will make it more efficient. But I'm not going to talk about universal consensus here. All right, let me first talk a bit about universal language machine. What is the problem with the current approach and how we fix that problem? The current problem, why we don't have, you may ask a natural question, why we don't already have all languages in the blockchain? Well, because a language is not just one little piece. It comes with an entire ecosystem of tools, of training, of auditing, formal analysis, and so on and so forth. And it takes a lot of time to develop these tools and to maintain them and to integrate them in your ecosystem. So this is the problem. The problem is that you have too many cross-cutting features, cross-cutting dependencies between languages and tools for them, including interpreters and compilers. All these require manual effort, manual implementations, and very specific, language-specific decisions. So instead what we do, we build on more than 50 years of research and engineering in the domain of programming languages, which for some reason, I would say almost ironically, is almost completely ignored by the Web3 space. Okay, so this is called formal semantics, and we have formal semantic frameworks, like the K framework that I invented 20 plus years ago when I was at NASA. So what these frameworks do, they allow you to define mathematically a programming language once and for all. And when I say mathematically, it's literally a mathematical theory associated to the language. You have the mathematical definition of EVM, the mathematical definition of Python, mathematical definition of Java. And now once you have this mathematical definition, you can push a button in the framework and generate the tool that you want for that language, like an interpreter or a compiler for that language. And that will be correct by construction. That means that everything that tool does, like an interpreter executes programs, it will come with a mathematical proof of correctness, why that execution is correct. So you are not at the odds of some ad hoc implementations of the language. And again, this is a very old field, probably the oldest field in computer science. The first papers in this field were published in 1960s, right? And there is a lot of research and a lot of Turing awards given to people who made contributions to this field. And again, to my big disappointment, this is not almost at all used in the blockchain space. And we want to bring it and get together with all the benefits. So, I have to go here again. So now that brings me to, I kept saying proofs, right? Because there are proofs underlying everything. And now our company is called Pi2 from proof of proof. So what is that? It's a zero-knowledge proof of mathematical proof. Okay, so under the hood, everything, computation, is reduced to mathematical proofs. And then a zero-knowledge proof of the mathematical proof will be generated that acts as a succinct correctness certificate for the claim that you are making. I know this is a small font. I don't expect you to follow the entire narrative here, but go from scan it from left to right. To the left, you input your programming language and your program and the execution environment. Same like what you would expect in a computer to run a program. And to the end, you have a proof, a zero-knowledge proof that the execution of this program happened correctly. It's same like in verifiable computing. But the big difference is that this works with all languages. Okay, so let me repeat, this is not for RISC-V, not for WASM, not for Cairo. It is for any programming language, including C, Java, and everything. Okay, and another thing that is important to notice on this figure is that in the middle we have a mathematical proof, this big pi. Okay, so this factors whatever the framework does and eliminates the execution environment completely from the trust base. I do not have to trust the interpreter. I do not have to trust the compiler. I do not have to trust the execution environment at all. Why? Because its job is to generate a mathematical proof for me that I can check now independently. Okay? And that's what gives us correctness by construction, what we call correctness by construction. And now once you have the mathematical proof, actually, believe it or not, it is a lot easier, like orders of magnitude easier to verify a mathematical proof, a rigorous mathematical proof, than to verify a computation of a program in some programming language. Because the mathematical proof has all the details to the last level of atoms in the proof. It's very easy to check every single step. And because of that, we eliminate completely from the trust base all this part, which is very complex. Okay? Compilers, interpreters, they always have bugs. And now once you have the mathematical proof, what you can do with it? Well, I can give you the mathematical proof as a correctness certificate, and you can do whatever you want with it. You can use it as a proof why what you claim is correct. But you can also check it with a zero-knowledge circuit that will generate a cryptographic proof of integrity for the mathematical proof. Hence, Pi2, proof of proof. Okay, so you generate a cryptographic proof that Pythagoras' theorem is correct, or that Alice transferred one token to Bob. Okay, so whatever you have a mathematical proof, you can now generate a zero-knowledge proof. All right, so this is the foundation of what we call verifiable computing 2.0, because we believe that the field of verifiable computing needs a serious overhaul. Currently, it is very specialized to very specific languages or VMs. And we know that that comes with lots of problems, in particular errors, in particular customization that doesn't have to be that customized, can be more general. In particular, I cannot use your ZK VM with my language and so on and so forth. We want to put a stop to that. We believe that going through mathematical proofs gives us a clear separation of concerns. Okay, so I separate the concern of correctness of the program execution from the concern of generating a ZK proof that it is correct, as opposed to mixing them together and developing something very hard to verify. So we believe we'll see more about this topic in the scientific field, because this is the way to go, period, in verifiable computing. So now, the elephant in the room, performance. You'll say, yeah, everything is beautiful. Mathematical proofs everywhere, correctness everywhere. There is a catch somewhere. There is a price to pay. Performance. Right? This is going to be dead slow, right? Right? There are 3 points of concern here. The first one is even the basic interpreter. Suppose that you give me a mathematical definition of a language and I use it as an interpreter. I run programs with it. That sounds horribly slow, right? Because you use a mathematical definition to run programs. That must be slow, okay? Then the second thing is, okay, so you use a logical proof engine, mathematical proof engine, and you prove, indeed, the execution. But then what if I want to extract an actual mathematical proof, to put it on my hard drive or in my pocket and to have it as a proof? Right? So that must be expensive, right? To extract the mathematical proof from the prover. And finally, we all know the ZK is slow, so if I want to generate a ZK proof, now it's going to be that slow. Okay? So let's start with the first step here. This is the first experience that you have when you use a language framework as opposed to a conventional interpreter. How many times do you think the interpreter generated from the semantics, formal semantics of a programming language, is going to be, how many times slower is going to be than a conventional interpreter? Let's take EVM, and let's take get. Right? You can run programs with get, or you can run programs with this mathematical infrastructure. How much slower do you think the mathematical infrastructure is going to be compared to get? A guess. Who thinks 100 times? Who thinks 10 times? Okay, who thinks comparable? And now here's the key question. Who thinks it will be faster? Nobody. Okay? Well, we ran lots of experiments. This is a summary of the big idea. So this is a program that runs 1,000 unit swaps, right? If you compile it normally with the Solidity compiler and run it with get, you get 250 milliseconds. Now, the exact same program, now we execute it with the formal semantics of Solidity. I don't even take the risk of a compiler to compile the program to EVM. By the way, my company, Runtime Verification, that PySquare spin off, does security auditing. And we found more than 20 bugs in the Solidity compiler. So compilers have bugs, okay, period. So now we don't want to take that risk. So we execute the program directly with the Solidity semantics, and 259 milliseconds, so it's only 5% slower. And you have the guarantee of correctness. But here is the interesting thing. Now, once you execute things in mathematics, you can do optimizations at the level of mathematical proofs that you cannot do in a compiler or an interpreter. Okay? And a very simple automated, it's called symbolic summary of basic blocks. By applying that optimization, we reduce to 152 milliseconds. So faster than get. So whoever tells you that formal semantics is slow, that going through mathematics and mathematical reasoning is slow, tell them no, that not anymore. Okay? Now we have performance. Performance is not the problem anymore. All right, but now how about the second step, generating mathematical proofs? This is where we incur a 10x overhead currently. And not because it is hard to get a mathematical proof, but because it is hard to log it. If you want to extract anything, if you want to make any program log something detailed, it will take time and space. But we know how to improve that. That will get faster. Now let's get to ZK very quickly. So the third component is the proof, mathematical proof checker implemented as a ZK circuit. We implemented it in every single ZK VM that we could run. And they are not that easy to run. The teams are very friendly sometimes. Sometimes they get fed up. They say, okay, we don't know how to help you from here on. But this is the bottom line. We have actually the capability to produce ZK proofs using any of the existing ZK VMs. Some of them are faster than others. Some of them we managed to make them faster than others. Some not. The best experience we had so far was with RISC-0 run on GPUs. Then immediately SP1, which we couldn't run on GPUs, just on CPUs, and so on and so forth. It's a pity we couldn't manage to make Cairo run at the expected, what we expected. We had lots of hope that it would be really fast. But anyway, the bottom line is that, again, to get back into the big picture, universality. Universality with respect to languages. You can plug and play any programming language. Programming language is not a big issue anymore. Second, you can get proofs of correctness using any proving methodology, including mathematical proofs and ZK proofs. And there is also consensus, which is universal, but I'm not going to talk about that. Now, a few words about the universal settlement layer and how we can bring actually all this to your blockchain. Okay, so we identified, I can say it in words because slides are harder to follow. So we identified the minimal API that you need in order to have all this functionality to your blockchain, whatever blockchain you pick. You have a smart contract, and you can submit transactions in any programming language through that contract. Okay, and the idea is to settle them as claims, which are mathematical theorems that have mathematical proofs and everything I showed before. But the bottom line is that they are code together with pre-state and post-state, and this can be verified completely independently of each other. Once you verify them, you can use them wherever you want, right? So the state of the USL is actually a set, not a chain, a set of claims with their proofs. And then there is a proof of inclusion. So once you verify a claim, you generate a claim, generate the proofs, verify it with whatever provers you want. Once you have a proof of correctness, now that is included in the state of truths of the USL. And now you get a membership proof, which is very succinct and very fast to verify. And that's the only capability you need to implement on your target chain in order to have access to all this functionality. And with this, I'm going to take maybe 2 questions or 3 questions. I have a couple more minutes. I invite you, if you want to see a demo of all this, we invite you tomorrow to this workshop. We'll show it live, how you can, we'll support 3 languages already. I don't tell you which, so you come. And we are going to plug and play a 4th one as part of the workshop. They speak another language, just plug it, and now voila, you can write smart contracts in that language as well without touching at all the network or upgrading anything. Questions, please? Anything? Yeah.
Yeah, guys, if you want to ask any question, we have like a minute or 2. So, anyone? Yeah. Can I? Yeah. Just wait.
Yeah. Ask and I will yell and I will repeat the question.
Working? No. Yeah.
There is no dumb question.
So in terms of interpreting this, implementing this at project level, we currently have a suite of tokens that we're developing on EVM and Solidity, or they'll be run across a whole bunch of different chains.
Yes.
It's predominantly OFT20 standard, so EVM compliant, but on layer 0. If we wanted to deploy code which is very similar on Solana and Rust,
Yes.
then what are the kind of mental steps that we'd have to go through? Do we have to re-architect our protocol? How simple is it to plug in?
So you have to re-architect also the code, right, in a different language, or you only architect
So I guess we have the flow in mind, like
Yes.
it would follow the same flow as our engagement with Solidity contracts on, say, Base or something, but it would have to be in Rust. Now, we wonder whether we could just remap the contract addresses to trigger different contracts to the Solana counterpart, but we write the fundamental code still in Solidity, and it executes into Solana.
Yes, that is possible, but we don't recommend that path at all. That's what I've done all my career, compilers and translators from one language to another. They are buggy, they are hard. So what we want to do is to plug and play your language. If you want Rust, just take the semantics of Rust and now execute things only in Rust. And that's it. No need to translate to any common VM. Actually, we have no VM at all here. There is no VM. There is a meta VM, if you want, the K framework that generates an interpreter for every language and so on, interpreter of an interpreter, but you don't have to pay a performance price, as I showed. So I personally do not recommend translating from one language to another, unless you really, really, really have to, okay? And sometimes we do. But we can make it work without translating.
Got it. So we'd go through the process of decompiling it into logical statements, and then it should just basically flow on any language.
Yes, yeah.
Understood.
you don't even need to pre-compile it. You can, if it's written already in Move, take it in Move. If it's written already in Solidity, you can have it like that in Solidity and interpret it. In the end, you interpret it anyway. So even if you compile it, you still interpret. And it's actually slower if you want to generate ZK proofs to generate a ZK proof for EVM instead of Solidity directly, because there are more steps to prove.
Thanks so much, Grigore.